Okay, so let's start. So this is the sixth lecture of the CMSA and YMSC in Tsinghua lecture on history and literature on mathematical science. And Mike Hopkins is going to chair this session. Right.
Okay, thank you, Yao. It gives me great pleasure to be introducing Ralph Cohen today. Ralph is, besides being an important and influential topologist, he's one of my oldest friends in mathematics. Since that's ambiguous, what I mean by that is I've known him for a really long time. Ralph has long been a leader in our subject, and his charismatic personality has set a very congenial tone in our field, and his interests have influenced many people to follow him in many directions. Looking forward to hearing Ralph talk about immersions of manifolds and homotopy theory.
Well, thanks, Mike. And I did understand you to mean that I'm one of your oldest friends. So thank you for that. And thank you also to Professor Yao for inviting me to give this talk. It's really a pleasure to do so. So the topic I'd like to talk about lies at the interface between the study of differentiable manifolds, differential topology, and algebraic topology. And this interface, I believe, has been one of the really the richest, most active areas of study in topology for many, many years, going back to the pioneering work of Thom, Pontrjagin, Milner, Smale, Novikov, many others. It's really been one of the driving forces in topology for all these years. And I find it kind of interesting that at one time, these two subjects were really quite different. Differential topology was much more analytic, studying singularities of differentiable mappings and the like. That's still an important part of differential topology, but at that time, that was really the main focus. Where algebraic topology at one time was very combinatorial, studying simplicial complexes and the like, and they were really very different subjects. But now there really is no clear boundary line between these fields. The study of manifolds has progressed tremendously using homotopy theory and algebraic topology over the years. And conversely, problems about manifolds has inspired the development of homotopy theory and algebraic topology more generally over the years. And these techniques that have been developed have found applications not only to manifold theory, but outside of topology in areas such as algebraic geometry and number theory, and even more recently in statistics and data analysis. Anyway, the focus today is going to be on the following kinds of questions. If you have two manifolds, and by the way, all the manifolds I'll talk about today are C-infinity differentiable manifolds, you can ask, does one manifold embed in the other? And more generally, you can ask about the topology of the space of embeddings of one manifold into the other. And you can ask similar questions about immersions. And I use this kind of hook arrow to denote an immersion because, of course, an immersion has the property that it's locally an embedding, but globally there may well be crossing points. And also, we'd like to study the space of immersions of one manifold and the other. For this talk, I'm going to mostly focus on the situation when the target manifold, the big manifold, is Euclidean space. Now, whenever addressing any kind of problem, a problem from differential topology or geometry or anywhere, from an algebraic topological viewpoint, the natural instinct of an algebraic topologist is to look for invariants or obstructions to doing the geometric construction, for example, and to be able to compute those invariants and obstructions. So in this case, that main invariant of an embedding or an immersion is the normal bundle of the embedding or immersion. So if in this case, if the normal bundle of an embedding in codimension K is a K-dimensional vector bundle, the fiber at a point X, which I called nu E of X, I'm not sure if you can see the cursor that I'm scribbling around with, but that fiber is the orthogonal complement of the image of the tangent space of the small manifold inside the tangent space of the big manifold. So all of those orthogonal complements fit together to give you a K-dimensional fiber bundle, and they satisfy an equation, a bundle equation that says the tangent bundle of the manifold, the small manifold, plus this normal bundle, that's the direct sum, is the tangent bundle of the ambient manifold, of course, restricted to M. And that we're going to come back to that equation over and over again. And as I said quickly before, an immersion also has a normal bundle. And that normal bundle is an invariant of an immersion or an embedding, because if you have two immersions, say, or two embeddings that are isotopic, meaning there's a one parameter family connecting to the two immersions, then their normal bundles will be isomorphic. So that's the sense in which they are an invariant of the situation. Now, whenever you have whenever you have an invariant, one can use it to describe obstructions to the type of construction you're trying to do. So for example, suppose you're just working in algebraic topology and working in bundle theory. And by hook or by crook, you're able to compute the minimum dimension K such that there exists a K-dimensional vector bundle over M so that the tangent bundle plus that vector bundle nu is trivial. This bundle equation again. If you can do that, and at K is this minimum dimension, then you can conclude that there is no immersion of M into codimension K minus 1. And the reason for that, of course, is that if there were an immersion into codimension K minus 1, it would have a K minus 1 dimensional normal bundle that would satisfy this equation. So because of that, we call any bundle that satisfies this equation a virtual normal bundle. Because a normal bundle satisfies this, you know, it has the property, when you add it to the tangent bundle, it's trivial. So in some sense, it's an inverse to the tangent bundle. Anyway, an amazing fact that is crucial to the study of immersions is a fact due to Hirsch and Smale. Smale and Hirsch, really, because Smale proved it first for spheres, is that the normal bundle is in fact a complete invariant of an immersion. So what do I mean by that? Let me just state their theorem. So you can look at the derivative map. So what does that do? It assigns to an immersion its differential, what it does on the tangent bundle level. So it's a map between the tangent bundles, which is injective or a monomorphism on every tangent space. So call that a bundle monomorphism. And that's what this notation reflects. And their theorem is that this derivative map just between these spaces, from the immersion space to this space defined entirely in terms of vector bundles, is a weak homotopy equivalence, at least for positive codimension. The amazing result, which tells us essentially that we can study immersions by studying vector bundles. And I want to go through that in some detail. The first application, though, of this result was really before it was proved in that generality, when it was known for spheres by Smale. And I write here that it was one of the most celebrated works of the 20th century, and I believe that. He classified immersions of spheres into Euclidean space. More precisely, he proved the following theorem. I'm stating it a little bit differently than the way he did, but it's equivalent. The first statement is a rather trivial statement, that the set of isotopy classes of immersions of a sphere into Euclidean space is the set of path components of this space of immersions. Because after all, if two immersions are in the same path component, then there's a path between them, which is a one parameter family of immersions connecting them, which is to say an isotopy. By the way, in the literature, isotopies of immersions are often called regular homotopies, and I think that was the language Smale used. Anyway, the crux of his theorem is the statement that pi 0, the set of path components, is this homotopy group. So this is one of the early areas in which the study of manifolds, in this case immersions of spheres, is directly translated into homotopy theory. In this case, the calculation of the homotopy groups of a Stiefel manifold. Vn n plus k is the Stiefel manifold of linear maps, which are monomorphisms from Rn to Rn plus k. You can think of that as the collection of n linearly independent vectors in Rn plus k. So quite a bit is known about the homotopy type of these Stiefel manifolds. This theorem, the way I stated it, is true for k bigger than 1. For k equals 1, his theory also describes some important result. So when you want to immerse the sphere in codimension 1, it says that the homotopy group of the Stiefel manifold, in this case, maps surjectively onto the set of isotopy classes of immersions. But of course, the Stiefel manifold in this case, collections of n linearly independent vectors in Rn plus 1, has the homotopy type of the orthogonal group, the special orthogonal group. So again, a fair bit is known about those homotopy groups. And in particular, since SO3, well, SO3 is one of all of our favorite groups. SO3 is homeomorphic to a projective space. And we know we can compare the homotopy groups of RP3 to S3 and conclude that its second homotopy group is 0. And the conclusion, because of Smale's theorem, if this homotopy group is 0, it says there's only one path component of immersions, which means the space of immersions of the two-sphere into R3 is path connected. In other words, any two immersions of S2 into R3 are isotopic or regularly homotopic. In particular, you can, and this is where all the press happened, you can isotope the identity immersion of the two-sphere, thought of as the unit sphere in R3, to its opposite, the immersion that sends T1, T2, T3 to its opposite. And such an isotopy is called an eversion of the two-sphere. And in colloquial language, it says you can turn a sphere inside out. So a couple observations about this theorem and about this application. The Hershmail Theorem was an early example of a theorem that's now referred to as an H principle. I think that term was coined by Gromov. It's been generalized, the H principles, that is to say, generalized and applied to a wide variety of circumstances over the years by Gromov and Elyashberg, Mishachev, Vasiliev, and many others. It's really an important tool in studying dynamical systems. It's an important tool in studying symplectic geometry. It's really had a tremendous amount of applications. The other thing I want to point out is that this homotopy theoretic argument that Smale used to show that there exists an eversion of a sphere in R3, of course, is not constructed. He did not describe a particular isotopy or regular homotopy between the identity and its opposite. But these kinds of eversions were eventually discovered, as we all know, and by several people that I've listed here. And now all you have to do is go to YouTube and you can watch a 2 or 3 minute video of the sphere being everted. But it was really a tremendous piece of work talking about, and also philosophically, and how you can study manifolds using homotopy theoretic methods. So now I would like to change direction slightly, because really any more modern study of immersions and embeddings goes back to Whitney's original work back in the 40s. As we all know, Whitney proved that any closed manifold embeds in Euclidean space of dimension 2n and immerses in dimension 2n minus 1. So that naturally leads to the question, is Whitney's result the best possible result? So let me phrase it this way. Let E of n be the smallest integer so that every closed n-manifold embeds in codimension E of n into Rn plus E of n. Whitney's theorem says that E of n is less than or equal to n. Now in very low dimensions, of course, for n equals 1 or 2, that's best possible. You can conclude E of n equals n, because of course the circle embeds in R2, but not in R. The Klein bottle or a real projective space is are surfaces that embed in dimension 4, but don't embed in dimension 3. Now, more generally, Whitney also knew in the same paper that projective space of any dimension of the form of power of 2, RPN for n 2 to the k, does not embed in dimension 2n minus 1. Again, he proved it embeds in dimension 2n, but it does not embed in dimension 2n minus 1 when n is this power of 2. And he proved that using a characteristic class argument. One of the first characteristic class arguments to obtain a geometric result. Characteristic classes he used are now called Stiefel-Whitney classes. So anyway, it says Whitney's theorem about embedding an n-manifold in R2n is the best possible theorem when n is of the form a power of 2. Now, it's also known that Whitney's result can be improved when n is not a power of 2. It's known that E of n, this best codimension, embedding codimension, is smaller or equal to n minus 1 if n is not a power of 2. And this is a result of Hefliger, Hirsch, and CTC Wall. But in general, if n is not a power of 2, a closed formula or even a conjecture for a closed formula is not only not known, it's not even, there isn't even a good conjecture, and it is a very difficult and deep question. Now, we can consider the corresponding question about immersions, and one can say a whole lot more, primarily, maybe entirely, because of the Hershmail Theorem that translates questions about immersions into questions about vector bundles. So I will call the corresponding number for the best immersion codimension phi of n, the smallest codimension into which every n-manifold immerses. And as I said, by Hirsch and Smale, we can translate that to a question about vector bundles. Namely, this number phi of n that we're looking for is the smallest integer so that this space of bundle monomorphisms I talked about is non-empty. The fact by Hirsch and Smale that the space of immersions and bundle monomorphisms are weakly equivalent at its very basic level says if one space is non-empty, the other space has to be non-empty. Now, let me kind of rephrase that corollary, because if you have a bundle monomorphism, the tangent bundle of a manifold into that of Euclidean space, then it determines, and really is determined by, a linear embedding, a linear monomorphism from the tangent space of X into Rn plus K for every point X in the manifold. So of course, you can take the orthogonal complement like we did before. I'll call that nu of x of this image of this linear embedding. And those orthogonal complements fit together to define a vector bundle that satisfies this equation that being the orthogonal complement at every point essentially will tell us that as a bundle, tangent bundle of M plus nu is trivial. In other words, as I said before, it is a virtual normal bundle of dimension k. But Hershmail theory says this virtual normal bundle is isomorphic to an honest normal bundle of an immersion. So Hershmail theory translates the question of finding immersions into Euclidean space into the question of finding these virtual normal bundles. So again, I can restate the Hershmail theorem, and it says the manifold immerses in Rn plus k if and only if M has a virtual normal bundle of dimension k, of a normal bundle, a vector bundle satisfying that equation. And it also therefore says that this number phi of n, the best immersion codimension that we're looking for, is also the integer, the smallest integer for which every manifold admits a phi of n dimensional virtual normal bundle. So again, the problem of finding immersions in Euclidean space has been translated into finding these virtual normal bundles. I want to reduce this problem one step further. Hirsch and Smale reduce it to a study of vector bundles. And as I mentioned before, a study of vector bundles is part of algebraic topology, indeed homotopy theory. And that translation from vector bundle theory to homotopy theory is a well-known construction, goes back to the late 40s, early 50s. And it's the theory of classifying spaces. So let me say just a few words about that because it'll be important in our study. So recall that for any topological group, there is a universal principal G bundle. So it's a principal G bundle. I'll tell you what I mean by universal in just a second. It has the standard notation. The base space is called BG, the total space is called EG, the universal bundle. So what does universal mean? Well, given a map from any space to the base space to BG, and by the way, I should have said this earlier, I suppose, by space, I always mean for this talk, and almost always, a space of the homotopy type of a CW complex. We want to rule out pathological spaces. So given a map from a space of this homotopy type of a CW complex or simplicial complex, by the way, manifolds, algebraic varieties, they satisfy this. We can consider the pullback principal bundle called F star of EG. And this induces a set map from, this notation means the set of homotopy classes of maps from X to BG to the set of isomorphism classes of principal G bundles. The reason it induces that kind of set map is a basic result in algebraic topology. It follows from the, I believe it's called the covering homotopy theorem that says if you have two maps that are homotopic, then their pullback bundles are isomorphic. So we induce a set map like this pullback map. And the statement that this bundle is universal is the statement that this correspondence is a bijective correspondence. It gives a bijective correspondence with principal G bundle to this set of homotopy classes of maps. So in particular, it says every G bundle over a space X is isomorphic to one that is pulled back via a map from X to BG. And these bundles, these universal bundles always exist and are unique up to homotopy. And the space BG is referred to as the classifying space of the group, because again, this bijective correspondence says that principal bundles are classified by maps into BG. Now, going back to immersions, we want to study, we have the Hershmail theorem that translates immersions into the study of vector bundles. I just told you about classifying principal bundles, but there is another rather elementary bijection that one can use, and that is for G equal to the orthogonal group, the set of isomorphism classes of principal ON bundles is in bijective correspondence with a set of isomorphism classes of n-dimensional vector bundles. And the way that correspondence goes is if you have a principal bundle, it has an action of ON on the right. So, and ON, of course, acts on Rn by matrix multiplication. So you can divide out by that common ON action, this diagonal action, and that defines an n-dimensional vector bundle. And it's very easy. It's usually an elementary exercise in a beginning algebraic topology class to show that that is a bijection. So putting those things together, one therefore knows that the set of homotopy classes of maps to the classifying space of the orthogonal group is in bijective correspondence to the n-dimensional vector bundles over X, isomorphism classes of such things. And that'll be very useful for us. Because it says that bundle theory can be studied via homotopy theory, and we know that immersion theory can be studied via bundle theory by Hirsch and Smale. So I want to make that more precise or more explicit. So I want to go back to Whitney. So we already know from the way I stated Whitney's theorem that any manifold immerses in Euclidean space in dimensions large enough, embeds in fact, but he actually proved more. His technique proves much more. In particular, it will prove that if we increase the dimension of the Euclidean space, then any two immersions become isotopic. So any two, not only does a manifold have an immersion or embedding into Euclidean space if the dimension L is large enough, but any two such are isotopic, again, if the dimension is large enough. So what does that mean in terms of this theory of classifying spaces of bundles when we talk about the normal bundle? Well, if you immerse the manifold into codimension L Euclidean space, L very large, then by what we just said, there is a classifying map, which is well defined up to homotopy, of the normal bundle of that immersion that I called nu ML. But notice, since L is large enough, sufficiently large we're assuming, any two immersions are isotopic, which would mean that the two normal bundles would be isomorphic. And that would mean by this classifying space theory that the two maps classifying these two different immersions would be homotopic. So for L large enough, the manifold comes equipped with a map to BOL, which is well defined up to homotopy. It's a homotopy, it's an invariant of the manifold. It depends on the differentiable structure of the manifold, but it is an invariant of the manifold. It classifies the normal bundle of an immersion into large codimension. Now, the way to keep track of these large dimensions is to take a limit over L, we call the resulting space BO. And what we've concluded from Hirsch and Smale and Whitney is that there exists a map that is well defined up to homotopy from the manifold to BO that classifies the normal bundle of an immersion into a large dimension Euclidean space. We call that the stable normal bundle map. Again, this map is well defined up to homotopy. It just depends on the manifold. So because of this, you can interpret the Hershmail theorem in this setting in the following way, and this will be quite useful for us. So the corollary says that a closed n-manifold admits an immersion into codimension K if and only if there is a map that I colored in blue from M to BOK, this classifying space, that makes the following diagram commute. Namely, you can take the stable normal bundle map, which is a well-defined map to BO. And the statement is that this map that we're looking for factors the stable normal bundle map at least up to homotopy. Algebraic topologists traditionally like to state results, like to think often in terms of commuting diagrams. And so I'm just really translating the previous statement using this classifying space theory into a statement about the lifting of the stable normal bundle map. The stable normal bundle map is an invariant, and the question is, does it lift or factor through BOK? If it does, then the manifold admits an immersion into codimension K, and that's an if and only if statement by the results that we've stated so far. Now, when you have a situation like this, that says you can admit it admits an immersion if and only if the following construction exists, then you can use that to find obstructions to finding immersions. Now in algebraic topology, I think much in algebraic geometry often too, obstructions occur, at least the first place one looks for obstructions is in cohomology. And in our case, the cohomology of these spaces is really quite nice, at least if you take Z mod 2 coefficients. The cohomology of BO is a polynomial algebra on infinitely many generators, Wi. Wi lives in HI, the dimension, and it's referred to this ith Stiefel-Whitney class. It's essentially the characteristic class that Whitney was computing. Furthermore, if you project this limiting space, BO, the cohomology of it, onto the cohomology of any finite BOK, then all the Wi's for I larger than K go to 0, and the Wi's for I smaller or equal to K remain algebraically independent, and the cohomology of BOK is the polynomial algebra also, but just on these first K Stiefel-Whitney classes. Now, as I said and wanted to make a big point of, every manifold comes with a stable normal bundle map. That's an invariant of the manifold. So you can look at that map in cohomology. And in particular, you can pull back in cohomology the image of one of these Stiefel-Whitney classes. And I will call that, it's often called WK bar of M. This is referred to as the kth normal Stiefel-Whitney class of the manifold. And the upshot of what we've been discussing is that if this cohomology class is non-zero, then M does not immerse in Rn plus k minus 1, codimension k minus 1. Because again, if it did, it would have a k minus 1 dimensional normal bundle, which would be classified by a map to be OK minus 1. And by these calculations, that would say that WK, the kth Stiefel-Whitney class, would be 0. So if it's non-zero, that gives you an obstruction to immersing the manifold into that codimension. For example, just going back to Whitney's work, Whitney essentially proved that if we take projective space in dimension n equals a power of 2, 2 to the k, then the n minus first, 2 to the k minus 1, normal Stiefel-Whitney class is non-zero in its cohomology. That's essentially what he proved. So we know from his theorem that this RPN immerses in R2n-1. But since this characteristic class is not 0, we can conclude that it doesn't immerse in one dimension less. In other words, his theorem in this setting, in this dimension, is best possible. So that says phi of 2 to the k is equal to 2 to the k minus 1. That is the best immersion codimension for n equals 2 to the k. And again, this was maybe a less well-publicized part, but certainly an important part of Whitney's theorem, of Whitney's paper. Okay, so now let's jump ahead a few years, not many. The next sort of important result in terms of finding obstructions to immersions in this setting was a theorem or a calculation of Massey, Bill Massey from Yale University, and I think it was published in 1960, that says that for a closed manifold, this normal Stiefel-Whitney class is 0 in a range. Now, again, we can conclude from Whitney's result, we know it's 0 for I bigger or equal to n-1, because Whitney showed that every manifold and manifold immerses in codimension n-1. But Massey says there's a larger range in general. It says Wi bar, this normal Stiefel-Whitney class, is 0 for I bigger than n minus alpha of n. Alpha of n is this funny number that pops up not only in combinatorics, but in this type of algebraic topology. It's the number of ones in the binary expansion of n. So if you write n as a sum of distinct powers of 2, then alpha of n is the number of distinct powers of 2. In other words, if you write n in base 2 as a sequence of 1s and 0s, it's the number of 1s. Now, Massey's result is the best possible in terms of finding these Stiefel-Whitney class obstructions by using the following example. So as I said before, write n as a sum of distinct powers of 2. So the number of distinct powers of 2, which I have as r here, is alpha of n. Then define a manifold to be the product of the projective spaces, each of which has dimension a power of 2. So it's a product of projective spaces of all these dimensions, and so it's an n-manifold. Now, as I said a moment ago, Whitney's calculation shows that W bar 2 to the I minus 1 of this 2 to the I1 projective space is non-zero. Similarly, the Stiefel-Whitney class of this dimension, 2 to the I2 minus 1, of the next projective space in this product is non-zero, and so on. And the way that Stiefel-Whitney classes behave with respect to products, one can see almost immediately that the Stiefel-Whitney class of the sum of these numbers of this product manifold is going to be non-zero in the cohomology of this manifold. Now, what is that sum? You add up all the powers of 2. By definition, that was n. That's the binary expansion of n. And you subtract 1 for every one of those powers. In other words, you're subtracting alpha of n. So this normal Stiefel-Whitney class in dimension n minus alpha of n is non-zero. And so Massey's result is best possible. It also tells us that there's an obstruction for this manifold to be immersed in codimension n minus alpha of n minus 1. So this result says that this best immersion dimension that we're looking for, phi of n, satisfies this following inequality. Phi of n is smaller or equal to n minus 1. That's Whitney's result. and phi of n is bigger or equal to n minus alpha of n, and that's Massey's calculation. Notice again, I will have now said the same thing several times, but in different ways. Notice that when n is a power of 2, alpha of n is 1, so phi of n has to be equal to n minus 1. Again, Whitney's result. Now, I want to restate Massey's theorem, again, in terms of a commutative diagram, because I believe, at least for me personally, it's conceptually a helpful way of thinking about it. Massey's result says that for every n-manifold, there exists a homomorphism from the cohomology of this classifying space, BO n minus alpha of n, to the cohomology of the manifold. It's a homomorphism of graded rings. Remember, the ring structure in cohomology is the cup product. And that homomorphism, it's just an algebraic fact, makes the following diagram commute. Well, we have this stable normal bundle map computed in cohomology. That's an invariant of the manifold. What Massey's theorem says is that that homomorphism of rings factors through the cohomology of BO n minus alpha of n. So there is this homomorphism of graded rings. It's well defined on the level of cohomology. Now, why is this a useful way of thinking about Massey's calculation? Well, because it sort of tells us what work we have yet to do. It tells us that if this homomorphism that I called theta m can be realized by a map, namely a map from the manifold to BO n minus alpha of n, which in cohomology is theta, that lists the stable normal bundle map, then this map to a classifying space would classify an n minus alpha of n dimensional vector bundle, which would be a virtual normal bundle in the sense that we described before, and therefore by Hershmail theory, it would classify the normal bundle of an immersion into R2n minus alpha of n. So Massey's result was cohomological. If we can realize his homomorphism by a map between spaces, we could say something about the existence of immersions. So that leads us to a conjecture called the Immersion Conjecture. It's often attributed to Massey. I personally don't know for a fact whether Massey explicitly conjectured this or not. But the conjecture says that this best immersion dimension, phi of n, is equal to n minus alpha of n. That is, every closed n-manifold immerses in R2n minus alpha of n. One would know that if such an immersion existed in general, that would be the best possible number because of the example I mentioned earlier, this example of products of projector space. The Stiefel-Whitney class gave an obstruction to immersing in one dimension less. So that's what the conjecture says. So now I would like to spend some time talking about a program that led to its solution. And whenever you're talking about a program that lies at the interface of differential topology and algebraic topology, or at least most of the time, as far as I know, you start with René Thom's work on cobordism theory. It's an essential piece of mathematics that allows us to study manifolds via homotopy theory. So let me just review a couple of those statements and then I'll describe the program. The first construction is something called the Thom space of a vector bundle. We're going to assume the vector bundle has a metric up to isomorphism. That doesn't matter much, but let's assume it has a metric, and we'll define the Thom space to be the unit disk bundle modulo the unit sphere bundle. So the unit disk bundle are all vectors in this vector bundle of length less than or equal to 1. And the unit sphere bundle are all vectors of length equal to 1. And so we divide out that sphere bundle and mod it to a point. It seems to be no standard notation for Thom spaces. I like this exponential type of notation, but there are many others. But this construction, I think, is very conceptual when the base space is compact, because when it's compact, this is just, I said equal to, I should have said homeomorphic to the one-point compactification of the total space of the vector bundle. So it's a natural construction, one-point compactification, but you see, using this a metric and defining the disk bundle mod the sphere bundle, we can perform this construction even when the base space is not compact, and we will have to do that in some cases. In fact, right away. So let's consider the universal vector bundle over our classifying space. I'll call that gamma n. So remember how that's constructed. We took the universal principal bundle, EON, and cross it with Rn and divide out by the common action over the orthogonal group, and that gives us a vector bundle over BON. And we'll let MON be the Thom space, disk bundle mod sphere bundle. MON, by the way, that notation does go back to Rene Thom. And one of the things that Thom proved in the mid-50s is that there's an isomorphism from homotopy groups to this differential topological classification of manifolds. So let me say that a little bit more carefully. You can take the homotopy group in dimension n plus k of one of these Thom spaces and take the limit over n, take the limit over k, and we call that the nth stable homotopy group of MO. Of course, many of you in the audience recognize what I'm doing here. There is an object that's a spectrum in the background, and this is the homotopy groups of that spectrum. But for these purposes, it's just a limit of these homotopy groups. And Thom's theorem says that this is in bijective correspondence, in fact, isomorphic as groups to the set of cobordism classes of closed n-manifold, where of course two n-manifolds are cobordant if there is an n plus one dimensional manifold with boundary whose boundary is exactly equal to the disjoint union of these two manifolds. Now notice this is where the word comes from, cobordant. Together, these manifolds they make up the border or boundary, cobordant. This is a group, the addition is can be thought of as disjoint union, and immediately one sees that it is a two group. In fact, every element of this group has order 2, because if you take a manifold and take its disjoint union with itself, that together forms the boundary of the manifold M cross an interval. So 2 times any manifold in this equivalence relation is 0. But this amazing theorem that this classification of manifolds up to cobordism can be computed using these stable homotopy groups was not only significant in the study of manifolds, but it really supplied a tremendous impetus to the development of homotopy theory. Now, if I take all of these homotopy groups together, or all of these cobordism groups together, really as a direct sum, then this becomes a graded ring where the product of manifolds is just given by the Cartesian product of manifolds. So now, not only did Thom describe this general procedure of studying cobordisms in terms of homotopy groups, he actually computed the darn thing. Now, let me just pause for a minute before I discuss this calculation. I should say that Thom's theorem generalizes in many significant ways. In particular, if you have a structure on the manifold, like an orientation or an almost complex structure or a framing, his theorem also says you can compute the cobordism groups of manifolds with that structure using stable homotopy theory. Indeed, in the case of manifolds that have framings, this was known and proved earlier by Pontrjagin back in the 30s in the case of frame manifolds. But anyway, let me go back to what Thom computed when you're not assuming any structure on these manifolds at all. They don't necessarily have to be oriented or almost complex structure or anything of that sort. He computed that this graded ring is in fact a polynomial algebra over Z mod 2. As I mentioned, every element in this group viewed as an abelian group has order 2, but this is much, much stronger than that. It says that you can compute that it's this beautiful polynomial algebra. Again, you have infinitely many generators in different dimensions, but you don't quite have one in every dimension. Namely, you have one generator in every dimension that is not of the form a power of 2. It's kind of an odd thing. For those of you who know, it has to do with the steam rod algebra. But anyway, so it says there isn't a generator in dimension 1. There is a generator in dimension 2. There is not a generator in dimension 3. There is one in dimensions 4, 5, 6, none in dimension 7, and so forth. By the way, once you have this calculation, you can immediately read off that this cobordism group in dimension 3 is 0, which is to say it has a geometric consequence that every closed 3 manifold is the boundary of a 4 manifold, right away from this much stronger calculation due to Thom. Now, from Thom's calculations, one actually can describe explicit manifolds that represent these generators, and this will be very useful to us in studying this immersion problem. So let me define a manifold that I'll call capital BR that represent one of these generators, little br. And I'll do it inductively or recursively. First of all, I'll just say right off the bat that the manifolds in dimensional power of 2 will be these same projective spaces that come up often. In more generality, I'm going to assume, if I want to define Bn, I'm going to assume recursively that Bk has been defined for integers less than n, and I'll then define Bn in the following way. So write n as a sum of distinct powers of 2 again. The number of distinct powers of 2 again is alpha of n. And this time I want to order those distinct powers of 2, say from smallest up to largest. So in particular, when n is odd, that first distinct power of 2 is that I1 would be 0. It's 1 plus 2 to the I2 plus everything else. But in any case, this tells us that we can write n as this first smallest distinct power of 2 plus an even number, where m is given by 1/2 of the remaining powers of 2. And so I can define Bn in the following way. Take the sphere of dimension 2 to the I1. And again, when n is odd, that sphere is just going to be a circle. And then cross it with Bm cross Bm, which inductively or recursively we assume has already been defined. And then we mod out by this common action of Z mod 2. Z mod 2 acts on this product of Bm by just flipping the coordinates, and it acts on the sphere by the antipodal map in the usual way. So these are my favorite examples of generators for this cobordism ring. There are many others. But what it says, amazingly, I just want to pause and appreciate what Thom's theorem says here. It says that every manifold is cobordant to one that is possibly a disjoint union and of products of these Bn's, and these Bn's in turn are products or these equivariant balanced products of spheres and projective spaces. So every manifold can be described in terms of these spheres and projective spaces. A really amazing result. Now, the way I want to use this result for our purposes is that from these specific manifolds, Bm, and using Whitney's theorem, it's quite easy to show directly that Bm, as an example, is a manifold that does in fact immerse in this dimension that we're interested in, 2m minus alpha of m. You show that because products of immersions, you can take products of immersions and even fiddle around with that equivariant product possibly. But anyway, the result, by taking disjoint unions and products of these immersions, you can come up with quite an easy proof of a theorem that was originally proved by Richard Brown that says every n-manifold is cobordant to one that immerses in R2n minus alpha of n. That doesn't prove the immersion conjecture, but it gives some evidence for it. And that brings us to a program of Brown and Peterson, Ed Brown and Frank Peterson, both of whom are local here, if you can say in the days of Zoom of being local. They were local to Boston. Brown, who was my thesis advisor, spent his career at Brandeis University. Frank Peterson spent his career at MIT. So let me describe their program. It started in the early 60s, and they considered this stable normal bundle map again. And they were looking at the map, induced map in cohomology. This is a map of graded rings. So if we look at the kernel, which I called I sub m, this is an ideal in the cohomology of BO, which is this polynomial algebra, as we've seen. Now, I should say that this ideal is non-zero. We know it's non-zero because Massey told us that the Stiefel-Whitney classes Wi for I bigger than n minus alpha of n are zero on every n manifold and therefore lie in this ideal. And that in fact says that if I define In to be the intersection of all of these ideals, then In is non-empty. Those Wi's live in In. What Brown and Peterson did just a few years after Massey was calculate the ideal In explicitly. It's really quite a beautiful calculation. I wanted to describe it explicitly here, but I think I decided not to because it really involves a lot of tools of the trade, such as calculations of the Steenrod algebra, how they act on Thom's cohomology of Thom spaces and the like. But it is really a very direct, beautiful calculation. It inputs Poincare duality into how the Steenrod algebra acts. And I'd really recommend it as must reading for any graduate student studying algebraic topology. But the upshot is that this stable normal bundle homomorphism from the cohomology of BO to the cohomology of M factors through by definition the quotient by this ideal. And again, Massey's result says that that quotient, the quotient map factors through the cohomology of BO n minus alpha of n, just algebraically interpreting Massey's result. Now, the next major step took a major leap beyond the realm of cohomology. About 10 or 12 years later, in the mid-70s, Brown and Peterson constructed a space that they called BO mod IN. You either like this notation or you don't. It's a little odd notation. Call a space BO mod IN. You're not modding out the space by any subspace, but they called it BO mod IN because this space comes equipped with a map to BO in such a way that the cohomology of this space BO mod IN is indeed the cohomology of BO modulo the ideal IM. And that's why they called it this space. So this space realizes this quotient of this polynomial algebra modulo the ideal. Furthermore, and more importantly, they show that for every n-manifold, there is a map from the manifold to BO mod IN that makes this diagram commute. Namely, you have a stable normal bundle map. What it says, what Brown and Peterson show, is that that map lifts to a map to BO mod IN. Now, what is the significance of that? Well, first of all, because that is true, because the stable normal bundle map always lifts through this Brown-Peterson space, they refer to this as a universal space for manifold normal bundle data, normal data. So what's the significance? It allows us to reduce the study of this immersion conjecture, for example, about the best immersion dimension for all n manifolds to a homotopy theoretic question about this Brown-Peterson universal space and this map to BO. The immersion conjecture is a conjecture about every n manifold. So we don't no longer have to look one manifold at a time. We can look at this single space and this map to BO. Let me say that more explicitly. So here's a question. Is there a map from this space BO mod IN to BO n minus alpha of n that lifts the Brown-Peterson map to BO? So that's a question purely in homotopy theory. The title of this talk is Immersions of Manifolds and Homotopy Theory. This is purely a question in homotopy theory. And notice that if the answer to this question were yes, then I could take this Brown-Peterson map from BO mod IN, from any n manifold to BO mod IN, compose it to the map that answered this question to BO n minus alpha of n, and the composite would classify a virtual normal bundle. And therefore, by Hirsch and Smale, again, we haven't forgotten them. Their work is central to all of this. By Hirsch and Smale, it would say that it would classify the normal bundle of an immersion into dimension 2n minus alpha of n. So that's the tact we're going to take. So the theorem from the early 80s, it was that such a lift exists, and therefore you can conclude the immersion conjecture is true. So I know it's an hour now, but I would like, with your permission, to take a few minutes describing some of the ingredients of the proof of this theorem, and then I'd be happy to answer questions and go on from there. So the proof is by obstruction theory. It's long and technical, but it's an obstruction theory that is classical in some sense. So let me describe some of the ingredients of the proof and how it went. The obstruction theory it uses is a classical bit of machinery called the Moore-Postnikov tower. It is a tower of fibrations that starts, base space is BO, and the limiting space, or the total space, is BO n minus alpha of n. And it's a tower of fibrations, a sequence of fibrations, x1 fibers over BO with fiber K1, x2 fibers over x1, xj fibers over xj minus 1, fiber kj. These are all fibrations, and one of the main features is that the fibers, Ki's, are Eilenberg-MacLane spaces. Now, many of you are very familiar with those. If you're not, the main upshot of that is that if you have a lifting to the J minus first stage, the obstruction to lifting it to the J stage is cohomological. That's the main upshot. So the structure of the proof is an inductive proof. It assumes this map to BO that Brown and Peterson described lifts to the J minus first stage of this tower, and one wants to look at the obstructions to lifting it to the J stage of the tower. Now, I should say right away that that's not a well-defined problem in the way I said it, because it is quite possible, in fact, I believe it to be true, that there exists a lifting to the J minus first stage that in fact lifts to the J stage. But if I took some other lifting, that other lifting may not lift. So it's not a well-defined problem. So the construction of the inductive argument is much more detailed and involves more ingredients. And I'd like to spend 5 minutes telling you about those ingredients, and then I'll pause for questions. So the first thing I did was study the analogous problem on the Thom space level. And that's why I spent the time to introduce Thom spaces. So these are all maps to BO, so they all have bundles over them. They're really virtual bundles, so I'm gonna slough over that point. But they all have Thom spaces, again, really Thom spectra, that start with MO, the Thom space of BO or Thom spectrum, and end with MO n minus alpha of n, which I realize now that I probably should have used slightly different notation, because here I'm referring to it as a Thom spectrum. But anyway, so you get a tower of maps between spaces. You can, using the magic of homotopy theory, translate those maps into fibrations without changing the homotopy type and look at the fibers called homotopy fibers. They are not the same as what we started with, because applying Thom spaces does not preserve vibrations. But using how the Steenrod algebra, the algebra of cohomology operations, interacts with the Thom isomorphism, the first thing you can do is you can identify those fibers directly in terms of the original fibers in a large range of dimensions, at least sufficiently large range of dimensions. And by inputting Poincare duality and cobordism arguments using those same generators for Thom's cobordism ring that we used to prove Richard Brown's theorem, it is much less difficult. There's still some work to be done to prove that there exists a lifting on the Thom space level from the Thom space of BO mod IN, which you call MO mod IN. And furthermore, you could classify those liftings well. This also used Brown and Peterson's explicit construction of BO mod IN. And I should say, their construction really wasn't very explicit. It was more obstruction theoretic, proving that a space with these properties existed. However, the Thom space of the bundle turned out to be very explicit, and you can study that in a hands-on way. So this led to a lifting on the Thom space level. We wanted a lifting on the base space level. So we need a way of taking that Thom space argument and de-Thomifying it. And I must say, I remember from 35 to 40 years ago thinking about this, I really thought about it as, can we find an obstruction theory to de-Thomifying maps of spaces? And I was never able to set it in terms of a theory like that, but that is how I thought about the problem. And to do so, in this case, I used a couple more ingredients. One is what's called a stable lifting. So again, many of you are familiar with this, but in case you're not, given a space with a base point, you can suspend that space. And here's a picture. And you take two cones and put them together and you suspend them. And in order to preserve the base point, we also take the line that goes through the base point and identify it to a point. And that's called the suspension, sometimes the reduced suspension. A theorem of Snaith that had been proven 5 or 6 years earlier said that if I'm willing to suspend BO a number of times, it splits apart into much easier pieces. BO, remember, was a limit of spaces. BO1 sat inside BO2, which sits inside BO3. And so you can take the subquotients of that filtration, and you can take their one-point unions. That's what this symbol means. They all have base points, so you just take their union along the base points. Homotopy theorists call that a wedge sum. I hesitate to call it that because geometers and differential topologists who use differential forms think of wedge in a very different way. But anyway, it says that this space BO that we're looking at splits into these pieces that are much easier to understand. It's somewhat analogous to a group, a situation where a group splits into the subquotients of a decomposition series. Anyway, we understand that these subquotients through a large range of dimensions very well. And so this led to a much easier argument that says, well, we don't initially have a map from BON to BON minus alpha then that we're looking for, but if you set suspended sufficiently many times, you can. And so it gives a stable version of this lifting, which again is more evidence for the conjecture. So at this point, we have the Thom space level lifting, we have this stable lifting, we also have the argument on the cobordism level. What we really need, what I really needed back then, was something about the cell structure of the BO-mod INs to use this data to show that that lifting existed. And I wasn't able to describe it quite in those terms, but I did observe that there are multiplicative structures which somehow dominated the cell decomposition in a way. There were multiplicative structures such as maps from BO mod IK across BO mod IM to BO mod IK plus M. And similarly, BO mod IK squared extended over this balance product with a circle. Many of you will recognize this as something that suggests an operad. I never proved such a structure. These multiplicative structures were only defined up to homotopy, but it was enough to somehow dominate the cell structure of the BO mod INs, so that if I inductively assumed that the smaller BO mod IKs had the appropriate lifting, and that lifting to the J minus first stage of BO mod IN preserved those liftings appropriately, we could then ultimately conclude that there was a lifting on the space level. And that led to the proof. Things took me a little bit longer than I had hoped. I had a few other things about newer directions the study of immersions and embeddings have taken, but maybe this is a good time to pause for questions.
Okay, thank you, Ralph. Maybe we can give Ralph a round of applause virtually. And well, I'm clapping. And so there aren't any questions in the Q&A, but if we do have a few minutes for questions, if someone would like to ask some, maybe you can just type it into the Q&A. So Ralph, one of the attendees has asked, what are the other directions?
Okay, well, I had hoped
that, right?
I could take 5 minutes just talking about a couple other directions. One is old, one is new. And I'm happy to talk about those. An old direction has to do, well, if you have a fixed n-manifold, you can ask what is the best immersion dimension for that fixed n-manifold. So I've been talking mostly about the question of the best immersion dimension for all n-manifolds, but suppose you had a fixed n-manifold. In general, that's a really difficult problem. And the corresponding embedding question is even harder. But for manifolds of the projective spaces, there was a whole lot of work done from the early 60s through the mid 80s, and even after that. We still don't have complete answers, but work of many, many people, Adem, Barrick, Davis, Gittler, James, Mahowald, Milgram, others, really established a lot of algebraic topology from studying this problem. They used homotopy theoretic obstruction theory, kind of the sort I've been talking about, except oftentimes it was based on different kinds of obstruction theory instead of cohomology that was the basis for the Moore-Posnikoff tower, for example, the obstruction theory I use. They used obstruction theories based on generalized cohomology, including stable homotopy, and even some unstable techniques. And I remember asking Mark Mahowald, who was a mentor of mine, Mikey, I know he was one of your advisors. He was really a mentor of all of us who grew up in algebraic topology in those days, even those older than us and those younger than us. And I remember asking him, is this question about immersions of projective space so compelling that all this research effort was spent on it? And he said, sure, knowing the best immersion dimension for projective space is quite interesting. But really, the most interesting part is that if you want to understand obstruction theory of whatever sort you have, the projective space immersion problem was a good test ground for that obstruction theory. And so again, this play back and forth between homotopy theory and manifold theory was really on display in this project. Let me say probably the strongest immersion results or non-immersion results for projective spaces are due to Davis in the mid 80s. If you go to his website, he has tables for the best known immersion and non-immersion results. This is an example of one of the stronger results. I'm not sure it's the strongest possible. I won't even read it, but even in simple cases, it gives interesting results. But I would like to say a more recent direction in the study of immersions and embeddings is due to Goodwillie and Weiss. And many of you know about this, but it wouldn't be a good talk on immersions and embeddings if I didn't mention this work that really comes in the last 20 years or so. The goal here is to study the space of embeddings in terms of the space of immersions. Immersions are viewed as, well, we know a lot more about them because of Hirsch and Smale. It's translated to vector bundle theory. And in fact, there's a precise sense that Goodwillie and Weiss make sense of that says that the space of immersions is a linearization of the space of embeddings. And they develop an obstruction theory that's known as the Goodwillie-Weiss embedding calculus. And their obstruction theory is based on a resolution of a functor. The functor is from the category of open sets in the manifold to the spaces, and it sends an open set to the space of embeddings of that open set in Euclidean space. Now, when that open set is a disk or maybe a disjoint union of disks, one knows a fair bit about that embedding space. These are configuration spaces that have been studied quite a bit. So they develop an obstruction theory that's not based on cohomology, but the topology of these spaces of embeddings of disjoint unions of open disks. But it is a tower of fibrations that converges to this embedding space, and the base space in this case is in the space of immersions. So let me end by just giving you an example of some results that have come about using this more modern theory. Brian Munson, who was a student of Goodwillie, gave a complete obstruction to the following problem. Suppose you have an immersion of M into Euclidean space. The question is it isotopic to an embedding a natural question. He gave a complete obstruction to that problem in a range of dimensions that extended classical work of Heffliger using this Goodwillie-Weiss calculus. Ismar Volic, who was another student of Goodwillie, studied the space of knots. So that is the space of embeddings of the circle into 3 space. Now, classically, knots are the study of the space of isotopy classes of embeddings, which is pi 0. So, but the topology of the full space of embeddings, or the full space of knots, is quite an interesting object to study. And he related the Goodwillie-Weiss calculus to the finite type knot invariance of Vasiliev. Aron, Lambrecht, and Turchin used the Goodwillie-Weiss theory to study the difference between embeddings and immersions, and they calculated the rational homotopy type of that difference, which is to say the fiber, homotopy fiber, at least in this range of dimensions when L is large enough. Now, I'm gonna remind you, Whitney taught us that when L is large enough, you can embed any manifold. But that in and of itself doesn't tell us a lot about the topology of the space of embeddings. Using this theory, these 3 authors did tell us a lot about the space of embeddings, at least the rational homotopy type. And they also, in somewhat different combinations, combined this with work of Kontsevich to calculate the rational homotopy type of the space of long knots in Euclidean space in higher dimensions. Now, as I said, a knot is an embedding of a circle. A long knot is an embedding of the real line, so long as outside some finite interval, the interval might be very, very large, but outside some finite interval, the embedding is standard. So it's called a long knot, and they calculated the rational homotopy type of the space using Goodwillie-Weiss theory as well as work of Kontsevich. Finally, a former student of mine, Robin Koichev, related Goodwillie-Weiss obstruction theory to the Taub's integrals, which were defined analytically, giving invariance of knots. He related these analytically defined invariants to the Goodwillie-Weiss homotopy theoretic invariance, which allowed not only their generalizations, but their calculations in some case. Okay, I do think I will end here then. Thank you again.
So I think there's a couple more minutes, and I have a question, Ralph. Are there different or known results if you change the kind of manifold you're looking at? For example, for oriented or spin manifolds or symplectic manifolds?
That's a really interesting question. And the answer is a little bit, but only a very little bit. Actually, my very first student at Stanford wrote his thesis on trying to do the Brown-Peterson characteristic class calculations for almost complex manifolds using almost complex cobordism, or as you know, BP. And he actually ended up using Morava K theory. So he was able to get, so this is 25 to 30 years ago, goodness. He was able to get relations among characteristic classes from Morava K theory, so for almost complex manifolds. Not a lot else is known, in part because, and I might be wrong about this, but I don't think even getting started, like the characteristic class obstructions, are well understood in most settings. Like, you know, what is the analog of the ideal IN that Brown and Peterson calculated when you have manifolds with certain structure on the tangent bundles? I don't believe even those calculations have been done very much. So again, answer is very little is no.
Okay, thank you, Ralph. I guess there's one more question. I was typing an answer out, but maybe I'll let you field it. Is there any possibility of putting an E1 structure on the BO mod IMs?
So I believe so. In fact, I believe, in fact, Mike, you may remember a year and a half ago, we chatted about this quickly. I believe there should be some kind of E2 structure, probably the structure of an E2 module over an E2 algebra, of where the algebra is these configuration spaces. You know, I wish I could have written that down. I didn't know how to do that then. I still don't know how to do that. You need some kind of concrete models for these BO mod INs. One way to perhaps get at it, or at least some technology that one might use, is this, you know, these new results about EN cell decompositions due to Galatius and Randall Williams and Cooper's. Because like I mentioned during the talk, back 35, 40 years ago, I really was yearning for a good cell decomposition of BO mod IN, and I didn't have it. And that might be approachable now. One might also use some kind of infinity language so that one doesn't need these structures on the nose, but only up to homotopy, but in a controlled way that infinity operads could give you. I'm not sure, but I do think that there is hope in doing that.
Okay, thank you, Ralph. I guess if there's no further questions, we're almost at the time. Maybe we can give Ralph another round of applause. I don't know if you can hear that out there.
I hear every one of them. Thank you.
All right. Ryan or Yao, I don't know what the custom for closing this is now.
It's pretty late where Yao is now, so if there's nothing else from your guys' part, it's just a big thanks to Ralph for his talk and for being here. And we'll just close it at that.
Okay, thank you all.
Thanks.